All right, let's play clinical detective for a bit. We're going to crack a case where just one single clue, one, can point to a major diagnosis. And that clue? It's your urine pH. It's like a secret message sent directly from your kidneys. And today, we are going to learn how to read it.
So here's our game plan. We'll start with the main clue, then we'll check out the system that's supposed to be working. After that, we'll see what happens when it breaks, meet our suspects, and even look at some other culprits. Finally, we'll wrap it all up with why this whole thing is so important. Let's get right into it.
Okay, first things first. Every detective knows you have to understand your evidence. So what is this central clue, urine pH, really all about? So, on the surface, urine pH sounds pretty simple, right? It's just a number that tells you how acidic your urine is. You know, how many free hydrogen ions are floating around. But don't let that fool you. This one little number is actually a huge window into one of your body's most important jobs, keeping its acid-base levels perfectly balanced. And guess who's in charge of that whole operation? Yep, your kidneys.
Right, so before we can figure out who the culprit is when things go wrong, we've got to understand the scene of the crime when everything's running smoothly. So let's take a look at how the kidneys pull off this amazing balancing act every single day.
To really get what's going on, you've got to meet the cast of characters. There are four main players here, and they're all working together, or sometimes against each other, to determine the final pH. You've got the acid, the neutralizer, a real wild card we'll call the influencer, and of course, the foreman who's running the whole show.
First up, we've got hydrogen, the acid. This is pretty straightforward. The kidneys can literally pump these hydrogen ions straight into the urine. Now, the foreman I mentioned, that's a hormone called aldosterone. When aldosterone clocks in, it's basically yelling at the kidneys, pump more acid. And the more acid they pump, the lower the urine pH goes.
Okay, meet player number 2, ammonia. This is our neutralizer. The best way to think about it is like a fleet of garbage trucks. The kidney cells make this ammonia, and its whole job is to drive around, pick up those spare hydrogen ions, and haul them away. By binding to the acid, it neutralizes it, which makes the urine more alkaline or, less acidic.
And now for our influencer, potassium. And this is where things get really interesting. You see, high potassium levels in your blood actually stop the kidneys from making those ammonia garbage trucks. So if you have fewer trucks on the road, less acid gets picked up, right? And that leaves the urine more acidic. On the flip side, low potassium tells the kidneys to make more ammonia trucks, which makes the urine more alkaline. This whole backward relationship, it's a super important clue we're going to need later.
So we've met the whole crew, we've seen how it's supposed to work. But what happens when the system fails? This, my friends, is where the real investigation starts. So the main case we're looking at today is something called renal tubular acidosis, or RTA for short. Basically, it's a whole group of conditions where the main problem is that the kidneys just can't handle acid properly. That perfectly balanced system we just talked about, it's broken. And our urine pH clue is going to be the key to figuring out exactly what went wrong. Now, RTA isn't just one bad guy. It's more like a whole family of culprits. So let's do a classic suspect lineup. We'll bring them in one by one and use our pH clue to figure out their MO.
Okay, let's start with two of our main suspects, type 1 and type 4 RTA. Type 1 is pretty easy to understand. The pumps that push hydrogen acid into the urine are just broken. No acid getting out means the urine is alkaline. Makes sense. But type 4, now this is where it gets tricky and kind of cool. The problem here is that our foreman, aldosterone, isn't working. So you'd think that would also lead to alkaline urine, right? Less acid being pumped out. But here's the twist. Type 4 also causes high potassium. And what did we learn about high potassium? It shuts down the ammonia garbage trucks. So even though less acid is being pumped out, there's nothing there to neutralize it. And the result, weirdly enough, is acidic urine. It's a total paradox.
All right, on to our next suspect, RTI 2. And this one is a real chameleon. It's a master of disguise because its main clue, the urine pH, keeps changing. Sometimes it's acidic, sometimes it's alkaline. So how on earth are we supposed to catch a culprit like that?
Here's the secret to RTAI's disguise. It all comes down to bicarbonate, which is a base. In RTAI, the kidneys can't reabsorb bicarb properly. So in step 1, when there's plenty of bicarb in the blood, it just spills out into the urine, and poof, you get alkaline urine. But, and this is the key, once the bicarb level in the blood drops really low, below about 15, the body basically runs out of it to spill. At that point, the kidney's normal acid-pumping machinery, which was working all along, suddenly becomes the main player. And just like that, the urine flips and becomes acidic. It's this two-step process that makes its pH so variable.
Okay, let's pull up the final rap sheet for our suspects. This chart lays it all out. Suspect 1, RTAI, always leaves alkaline urine and is associated with low potassium. Suspect 4, RTA4, leaves acidic urine and has high potassium. And our shapeshifter, RTA2, variable pH with normal or low potassium. You can see how by looking at just 2 clues, urine pH and serum potassium, we can tell these culprits apart. Case closed on that front.
But hold on, our investigation isn't over. RTA isn't the only thing that messes with urine pH. This clue can actually point us to a totally different type of burp, a bacterial infection. Let's see how.
You know, most of the time when you get a UTI, the bacteria make things more acidic. But there's a special kind of bacteria out there that acts like its own little chemical factory, and it does the complete opposite.
Their secret weapon is an enzyme called urease. See, your urine is naturally full of a waste product called urea, and this particular enzyme, urease, has one mission in life: to find urea and just split it wide open. So here's the heist, step by step. First, bacteria like Proteus dump this urease enzyme into the urine. Second, the urease finds the urea and splits it. And guess what that creates? A whole flood of ammonia. Remember our neutralizer, the garbage truck? Suddenly you've got thousands of them. And third, all that ammonia just goes to town, soaking up every last bit of acid it can find. This sends the pH skyrocketing, making the urine super alkaline. So when you see a UTI with really alkaline urine, that is a massive clue pointing you right to one of these urease-producing bugs.
Okay, we've gone through the system, we've lined up the suspects, we've closed the case files. So what's the verdict? Why does any of this actually matter? What's the bottom line here?
Well, the pH of your urine has some really direct consequences. It's kind of a double-edged sword. On one hand, acidic urine can actually make kidney damage from certain drugs even worse, and it's the perfect breeding ground for things like uric acid stones. But on the other hand, alkaline urine, while it can help your body get rid of certain toxins, creates the perfect setup for a totally different kind of kidney stone, like calcium phosphate stones. So it's this incredibly delicate balance, and when it's off, there are real consequences.
So when you get right down to it, that little pH number is anything but simple, isn't it? It's this living, breathing clue, a dispatch coming straight from the front lines of your body's constant balancing act. It really proves that sometimes the most powerful tools we have are the simplest ones, the ones that have been right in front of us the whole time, just waiting for a good detective to come along and read the story. It really makes you think, what other huge secrets are just hiding in plain sight?